Hi everyone, welcome to Mostly Math. Today we're going to evaluate a very general class of integrals. In particular, we'll be considering this class of integrals, the integral from minus a to a with respect to x of some even function, which we're going to call capital E of x, to some other even function, which we're going to be calling lowercase e of x, to some odd function of x, which is the capital O of x, plus 1. Now, I know what you're thinking. These are very general functions, so how can you possibly have a closed form in it? The only constant is 1. Well, it's actually a very interesting trick. There is a Flammable Maths video about it. I'll be sure to provide a link in the description for this video. They're actually going to use a different argument than what we are. It's about the same length. If you had to guess which one's shorter, I would say that this argument that we're going to do is shorter. You can feel free to check out this video. And we're also going to be doing a few different examples as well. And just to remind everybody the definition of evens and odd functions. So even function is e of minus x is equal to e of x. And of course, odd function O of minus x is equal to O of x. And in general, easiest example of an even function is x squared, a parabola. Easiest example of an odd function is x, just a straight line. And that's actually why the functions even and odd have that in their name, since if you had a function x to the n, it's going to be even for n even, and it's going to be odd for n odd. And just another fun fact, it can also be shown pretty easily that any even function has a Taylor expansion with even coefficients. For example, cosine of x is the sum of minus 1 to the n, x to the 2n over 2n factorial. It's not unique to the cosine function. You can actually show pretty easily, if you want to, that any even function is going to have a Taylor series with only even coefficients. So this further solidifies why you would call these kind of functions even and odd. And basically, we can see from the graphs that they have the appropriate symmetries. If we have a value over here at x, it's going to be the same value here at minus x. Same thing over here, but negated. So you can see what we're talking about. Same but different. Same but different. Okay, let's go on to the main event. Just a brief refresher on even and odd functions. Okay, so we're going to start by doing the very obvious step of breaking the integral into two parts. One minus a to 0 and one 0 to a. I'm going to have integral here, minus a to 0 plus 0 to a with respect to x of our even function over some other even function to an odd function plus 1. We're going to write the negative integral in terms of the positive integral like you would typically do in this kind of a scenario. So let's go ahead and do that. We have minus a to 0 dx capital E over lowercase e to the O plus 1 can actually be related to the other integral if we let x go to minus x. When we do this, I'm also going to put a minus sign out front, actually before we perform the reflection symmetry, so we can get a 0 and a minus a up top. So minus 0 to a, since when you let x go to minus x, it flips the signs of the bounds as well. With respect to minus dx, we have our even function of minus x over some other even function, odd function, plus 1, and we see using the properties of even and odd functions, these are going to be the same. This is going to have a minus sign. These two minus signs actually cancel out, which is pretty cool. Comes integral from 0 to a with respect to x, even function over even function to the minus odd function plus 1. And now we can simply combine the results. We see that we're going to have a capital E factoring out from both integrals. So it's just equal to integral from 0 to a with respect to x, our even function, big E, and now we have 1 over e to the x o of x plus 1 over e to the minus o of x plus 1. Can't forget the minus sign, that's the whole point here. And we are going to evaluate this crap here and see if it simplifies nicely. Well, this is actually just going to be, we're going to put it over a common denominator, which is the product of these two denominators, by multiplying this by this. So we get e to the minus o plus 1, multiply this, e to the o plus 1, and the denominators, we multiply these two together. So we have e to the o, e to the minus o, which is of course 1. It doesn't matter that they're all functions of x. This is a property of exponentials that holds. So we get 1 plus e to the o plus e to the minus o plus 1. We see they're exactly the same actually. So all this crap actually cancels out. It just becomes, remarkably, integral from 0 to a dx of our capital E of x. Now, why is this remarkable, you might say? Well, a few things here. This is one. So it's remarkable because you started off with a very general integral with three arbitrary functions. And it turns out that if we just use this very simple trick of splitting up the integral and using the reflection symmetry, the final result doesn't actually depend on two of the three arbitrary functions up to parity, which is pretty cool. And if you watch the flammable mass video, he covers a similar integral. He covers minus a to a dx e of x over some number t to the o of x plus 1, which it still holds for, of course, since if t is just a number, then it's obviously even, since if we have the graph of a number, got some value t here, if we look at some point x, the value is going to be the same as the point minus x, since it's the same everywhere. So of course t is an even function. And that was cool by itself. And let's give some examples to show what we can do with these bad boys. So the first thing that I can see is we can make a lot of integrals be equal to 1. So 1 is integral of, if we start at the right hand side, the even function I'm choosing to be 1, 0 to 1 of 1 dx, which if we go to the left hand side now, we can actually write as integral from minus 1 to 1 with respect to x of any even function, which we can choose to be, doesn't really matter, any odd function plus 1. So we can see that the true beauty of this is not that it's equal to the integral of e, it's the fact that there's two unknown functions here. And we can plug in some simple examples of this if we want it to be 1. The first example that I can see, examples that it's 1. Yeah, I mean, you can choose even and odd functions from here, basically. If we just choose this to be a number e, and then the odd function to be x, or like in a book that I got this from, you can choose it to be 1 over x as well, plus 1. And you can even generalize this further if you wanted to put an even function up at top. you could evaluate this integral, minus pi over 2 to pi over 2, with respect to x, of cosine x over e to the 1 over x plus 1, which is pretty cool. This would just be the integral from minus pi over 2 to pi over 2, 0 to pi over 2, sorry. Which we can evaluate readily as sine x evaluated at pi over 2 and 0. 0 goes away, it just becomes sine pi over 2, which is 1. So you can actually show that that's 1 as well. A lot of integrals become equal to 1. And I want to show just another few simple examples. There are, of course, uncountably infinite many examples you can choose from. You'll be only limited by your imagination, basically. These are just ones that I came up with. You can also look at integral from minus 1 to 1 with respect to x of x to the 2n over, say, e to the sine x plus 1. Like I said, it doesn't matter what this function is as long as it's odd, and this one's even. And this is actually just going to be the integral from 0 to 1 of x to the 2n, which we can evaluate readily as just 1 over 2n plus 1. Notable special case, if you let n equal to 0, you have another integral that's equal to 1. It'll be the integral of, 1 over e to the sine x plus 1. Let's see. What else is cool? Yeah, you can also do interesting things like have all the functions be transcendental. You can also evaluate integrals like 1 is now equal to the integral from minus 1 to 1 with respect to x of cosine x to the sine x plus 1. Pretty wacky integral. Pretty wacky. And you can also do interesting things like replace this with their hyperbolic version, since those have the same parity. Do cos hx sine hx plus 1. And you can also put the good old x squared function here in the denominator, which is also equal to minus 1 to 1 back to x of x to the 2n sine x plus 1. Lots of crazy things, really. Like I said, only limited by your imagination. And yeah, I showed a bunch of examples where the integrals are equal to 1. There, of course, are other examples as well. Like with the x to the 2n, that's going to have, the fractional results as well. But I think this integral is really cool as well. There's also a book that covers this technique using a different method as well. It's called Inside Interesting Integrals. By Paul Nahin. I will also leave a link for this in the description. It's a fantastic book that contains many tricks. Not this one. In the book and the Flammable Maths video, they actually use a somewhat more complicated argument involving splitting it into even and odd parts, but you get the same answer regardless. And yeah, if you have any cool examples of functions that you can put in here, feel free to leave them in the comments. I'm sure anyone that watches this video can find some, since you just have to know some even and odd functions, and I didn't list that many here. So if you enjoyed this, want to see more integrals, please just like, subscribe to my channel. I'll see you next time.